Medieval farmers built some of the most fertile soil in human history. They did it without buying a single bag of fertilizer, without a synthetic chemical, without a supply chain, without a corporation telling them what their soil needed, and the 7 methods they used, methods that fed entire civilizations for centuries, are still available to anyone with land, patience, and the willingness to stop buying what nature has always provided for free. Big agriculture wants you to believe that without their products, your soil cannot produce food. Medieval farmers proved the opposite for 1,000 years. Before we get to the 7 methods, you need to understand the single principle that made all of them work together. Medieval farmers did not think about fertilizer the way we do. They did not think about adding nutrients to soil. They thought about closing loops. Every organic material that left the farm as food came back to the farm as fertility. Animal waste, kitchen scraps, crop residues, human urine, ash from the hearth, fish bones from the river. Nothing left the system permanently. Everything cycled back. The result was soil that did not just maintain its fertility over generations, it built it. Fields that had been farmed continuously for 200 years were often more productive than fields that had been farmed for 20. Because the biological infrastructure of the soil, the microbial communities, the fungal networks, the earthworm populations, the aggregate structure, was being continuously fed and continuously strengthened by the return of organic matter in every form available. Modern industrial agriculture operates on the opposite principle. Nutrients leave the farm as food and are replaced by purchased synthetic inputs. The biological infrastructure is bypassed entirely. The soil becomes a passive medium for chemical delivery rather than a living ecosystem generating its own fertility. The 7 methods that follow are not 7 separate tricks. They are 7 components of a single integrated system. A system that was self-funding, self-renewing, and self-improving. A system that cost nothing to run because it ran on waste. The most universal fertilizer in the entire history of human agriculture was available on every farm, every day, at 0 cost. And medieval farmers understood how to use it with a sophistication that modern organic agriculture is only now fully appreciating. Animal dung, but not fresh. Never fresh. Medieval farmers collected bedding-mixed manure from barns and stables and piled it in covered dunghills, protected from rain to prevent nitrogen leaching. They aged it for 3 to 12 months before application. Some estates built dedicated dung pits with drainage channels to capture the liquid fraction separately. The liquid was diluted and applied to fields as a fast-acting nitrogen supplement. The solid fraction was composted until it became a dark, crumbly, sweet-smelling humus. The chemistry behind this practice is precise. Fresh cattle manure contains roughly 0.6% nitrogen, 0.2 to 0.4% phosphorus, and 0.5 to 0.8% potassium by weight. But most of that nitrogen is in the form of urea and ammonium compounds that volatilize rapidly if applied fresh. Aging the manure allows microbial activity to convert those unstable compounds into stable organic nitrogen that releases slowly as plants need it. The organic carbon in aged manure does something that no synthetic fertilizer can replicate. It feeds the soil microbiome. Every ton of well-aged farmyard manure applied to a field introduces billions of bacteria, fungi, and actinomycetes that colonize the soil and begin building the biological infrastructure that makes all other nutrients available. Long-term studies comparing manure-amended soils to synthetic fertilizer plots consistently show higher microbial biomass, better aggregate stability, higher water-holding capacity, and lower erosion rates in the manured fields. Medieval farmers also understood species differences. Poultry manure, at 2 to 3% nitrogen dry weight, was the most concentrated and was reserved for vegetable gardens and high-value crops. Horse manure, rich in undigested plant fibre, was valued for its soil structuring properties. Sheep manure, deposited directly on fields through the practice of folding, where flocks were penned on fallow fields overnight, was the most efficient delivery system ever devised. No hauling, no spreading. The animal did the work. The folding practice was so effective that medieval estate records show fields that received regular sheep folding, maintaining yields for centuries without any other amendment. The sheep were not just fertilizing the soil, they were inoculating it with the microbial communities from their digestive systems, introducing a diversity of organisms that modern soil scientists now recognise as critical for long-term fertility. Every medieval household burned wood, every medieval household produced ash, and every medieval farmer knew that ash was not waste. It was one of the most powerful soil amendments available, capable of transforming the productivity of acidic, exhausted land within a single growing season. Wood ash is the mineral residue of combustion. When wood burns, the carbon and nitrogen volatilizes gases. What remains is a concentrated package of every other mineral the tree spent decades accumulating from the soil. Calcium at 25 to 50% of dry weight, potassium at 5 to 7%, phosphorus at 1.5 to 2%, magnesium, zinc, copper, boron, and a spectrum of trace elements that synthetic fertilizers do not contain. But the most important property of wood ash is not its nutrient content, it is its pH effect. Most temperate soils naturally acidify under continuous cultivation. As pH drops below 6.0, phosphorus becomes chemically locked in the soil and unavailable to plants. Aluminum and manganese become soluble at toxic concentrations. Beneficial soil bacteria decline. Mycorrhizal fungi, the underground networks that connect plant roots to mineral reserves, become less effective. Wood ash is highly alkaline. Applied at modest rates of 1 to 3 tons per hectare every few years, it raises soil pH toward neutral within weeks. Not months, like agricultural lime. Weeks. Because wood ash contains calcium oxide and calcium hydroxide, the most reactive forms of calcium which dissolve immediately in soil moisture and begin neutralizing acidity almost instantly. At neutral pH, the phosphorus that was chemically locked becomes available. The aluminum toxicity disappears. The bacterial populations recover. The mycorrhizal networks expand. The soil that was struggling to support crops suddenly becomes productive again, not because anything was added to it in the conventional sense, but because the chemical environment was corrected to allow the biological system to function. Medieval farmers broadcast ash from their hearths onto fields in late winter, before spring ploughing. They concentrated it on the most acidic patches. They mixed it into compost heaps to accelerate decomposition and raise the pH of the finished compost. They used it as a pest deterrent, sprinkling it around the base of plants to deter slugs and snails. And they did all of this with material that was produced as a byproduct of heating their homes. The fertilizer cost nothing because it was the residue of a process they were performing anyway. Medieval households wasted nothing organic. Kitchen vegetable peelings, straw from the barn, leaves raked from the yard, chaff from threshing, spoiled hay, wool clippings, even broken pottery and brick rubble, added to improve drainage and aeration. All of it went into the compost pit. Medieval Andalusian agricultural texts, including the 12th century treatise by Ibn al-Awwam, describe composting household and stable waste in extraordinary detail, layering green nitrogen-rich materials with brown carbon-rich materials, keeping the pile moist but not waterlogged, turning it to introduce oxygen and accelerate decomposition, adding broken ceramics to improve the physical structure of the heap. This was not folk wisdom. It was applied microbiology, practiced without the vocabulary of modern science, but with a precision that modern composting guides have not substantially improved upon. The hot composting process that medieval farmers were running generates internal temperatures of 55 to 70 degrees Celsius. At those temperatures, weed seeds are killed, pathogens are destroyed. The complex organic molecules in raw waste are broken down by thermophilic bacteria into stable humus compounds that persist in the soil for decades. Mature compost applied to soil at 5 to 10 tons per hectare raises organic matter content, improves aggregate stability, increases water holding capacity, and introduces a diverse microbial community that continues decomposing organic matter and cycling nutrients long after the initial application. Research consistently shows that fields receiving regular compost applications maintain higher yields over time than fields receiving equivalent nutrient inputs from synthetic sources, because the compost is building the biological infrastructure that makes all nutrients more available. The medieval compost pit was also a community resource. Village records from medieval England describe shared compost heaps maintained by multiple households, with contributions and withdrawals managed by the village council. The fertility of the entire community's fields was a collective responsibility, maintained through the collective return of organic waste to the land. Nothing was purchased, nothing was imported. The fertility of the soil was generated entirely from the waste products of the community that depended on it. Human urine is, by volume, one of the most nitrogen-rich substances that any farm produces continuously and for free. Fresh urine contains 15 to 20 grams of nitrogen per litre, primarily as urea. It contains moderate potassium and smaller amounts of phosphorus. Its nitrogen to phosphorus to potassium ratio of approximately 11 to 1 to 2.5 makes it a near-perfect balanced fertilizer for leafy growth. Medieval farmers across Europe and Asia collected urine systematically. In Japan's Edo period, urban night soil merchants operated licensed collection routes through cities, purchasing human waste from households and selling it to farmers in the surrounding countryside. The system was so economically significant that cesspool rights were included in property transactions. In medieval China, the collection and composting of human waste was a cornerstone of the agricultural system that allowed multi-cropping on limited land. In Europe, the practice was less systematized but equally widespread. Medieval agricultural texts describe mixing urine with water at ratios of 1 to 5 or 1 to 10 and applying it to vegetable gardens and orchards in spring. Vineyard records from medieval France describe urine applications as a treatment for vine diseases, an effect now attributed to the nitrogen surge and the antimicrobial properties of the urea compounds. The key to safe and effective use was dilution and timing. Fresh, undiluted urine applied directly to plant roots causes nitrogen burn. Diluted at 1 to 10 with water and applied to the soil rather than the foliage, it provides a rapid, soluble nitrogen boost that is immediately available to plant roots. Composted with carbon-rich materials for 6 to 12 months, it becomes a stable, slow-release amendment with no pathogen risk. Modern ecosanitation research has confirmed what medieval farmers knew empirically. Urine diversion systems that collect and apply human urine to agricultural land can supply a significant fraction of the nitrogen needs of a household garden from the waste produced by the household itself. The loop closes completely. The nitrogen that leaves the farm as food returns to the farm as fertility. Here is the fertilizer that required no collection, no processing, no hauling, and no application. The plant grew it, fixed it from the atmosphere, and delivered it directly to the soil when it was turned under. Green manuring, the practice of growing plants not for harvest but for incorporation into the soil. And the medieval three-field system built this practice into the fundamental structure of European agriculture. In the three-field rotation, one field in 3 was planted with legumes: peas, beans, vetch, clover. These plants form symbiotic relationships with rhizobium bacteria in their root nodules. The bacteria fix atmospheric nitrogen, converting inert nitrogen gas into ammonium compounds that the plant can use. When the legume is turned under, that fixed nitrogen is released into the soil as the plant material decomposes. High biomass legume cover crops can contribute 100 to 200 pounds of nitrogen per acre to the soil. That is equivalent to several hundred kilograms of synthetic urea fertilizer, delivered at zero cost with zero energy input, and with the additional benefit of the organic matter from the entire plant biomass, improving soil structure simultaneously. Classical sources confirm that Romans used lupine and vetch as green manures. By the 1st millennium AD, the practice was standard across Europe. Medieval agricultural writers, including Walter of Henley and Pietro de Crescenzi, described the legume rotation as essential to maintaining soil productivity. The three-field system that dominated European agriculture for 500 years was built around this principle. But the nitrogen fixation was only part of the benefit. The root systems of cover crops penetrated deep into the soil, breaking up compaction and creating channels for water infiltration. When those roots died and decomposed, they left behind a network of pores that improved drainage and aeration. The mycorrhizal fungi that colonized the cover crop roots remained in the soil after incorporation, ready to colonize the roots of the following cash crop and extend its access to soil minerals. Research confirms that cover cropping raises soil microbial biomass by 7 to 30% and increases long-term soil carbon levels. The medieval farmer who planted vetch in his fallow field was not just resting the land, he was actively building it. coastal and riverside communities across medieval Europe and Asia had access to a fertilizer so concentrated in nitrogen and phosphorus that it could transform poor, sandy soils into productive gardens within a single season. Fish waste, bones, offal, the parts of the catch that could not be eaten or preserved. Medieval cod fisheries in northern Europe left piles of fish scraps on fields as a matter of routine. Atlantic coast farmers in Britain, Ireland and France harvested seaweed and dried fish remains and applied them to their most demanding crops. In East Asia, fish pond sediments from carp aquaculture were dredged annually and spread on surrounding fields, completing the nutrient cycle between the water and the land. Dried fish meal contains 5 to 10% nitrogen and 3 to 5% phosphorus by weight. Bird guano, the most concentrated form of this category, reaches 8 to 21% nitrogen and 12.5% phosphorus. These are not dilute amendments. They are concentrated nutrient packages that release their content as soil microbes decompose the organic matrix. The phosphorus in fish bone and fish meal is particularly valuable. It is present as calcium phosphate in a form that soil microbes can access and convert to plant-available orthophosphate. Unlike synthetic superphosphate, which can become chemically fixed in the soil within days of application, the phosphorus in organic fish amendments is released gradually as the biological decomposition proceeds, matching the plant's uptake rate rather than flooding the soil with more than it can use. Seaweed, harvested from coastal margins and applied directly or composted, added a dimension that neither manure nor fish waste could provide. Seaweed contains over 60 trace elements, including iodine, boron, and a spectrum of minerals that are often deficient in intensively farmed soils. It contains alginic acid, a polysaccharide that improves soil aggregate stability and water-holding capacity. And it contains natural plant growth hormones, cytokinins and auxins that stimulate root development and improve stress resistance in treated crops. Irish potato growers applied seaweed for both fertilizer and disease suppression. The high mineral content of seaweed-amended soil produced plants with stronger cell walls and more robust immune responses to the fungal pathogens that devastate crops grown in mineral-deficient conditions. The medieval farmer living near the coast had access to a free, annually renewable, nutritionally complete soil amendment that washed up on the shore every day. The only cost was the labour of collection. The seventh method is the one that most completely bridges the ancient world and the modern science of soil biology. And it is the one that requires the least material, the least labour, and produces the most biologically active amendment of any technique in the medieval repertoire: fermented plant liquids. The practice of steeping plant materials in water, sometimes with urine or manure added as a nitrogen source, and allowing the mixture to ferment for days or weeks before application. Medieval farmers across Europe steeped nettles, comfrey and yarrow in water barrels. The resulting liquid, dark, pungent and biologically active, was diluted and applied to crops as a foliar spray or soil drench. Medieval Korean and Chinese farmers fermented rice wash water, vegetable scraps, and plant residues to produce microbial inoculants that they applied to soil before planting. The mechanism is now understood precisely. During fermentation, lactic acid bacteria, yeasts, and other beneficial microorganisms multiply in the liquid medium. They produce enzymes that break down the plant material, releasing soluble nutrients. They produce organic acids that lower the pH of the liquid, creating a medium that suppresses pathogenic organisms when applied to soil. They produce secondary metabolites including plant growth hormones, vitamins, and antimicrobial compounds that stimulate plant growth and soil biological activity simultaneously. Comfrey, one of the most commonly used plants for fermented liquid fertilizers in medieval European gardens, contains a nitrogen to phosphorus to potassium ratio that closely matches the nutritional requirements of fruiting vegetables. Its deep taproot mines minerals from subsoil layers that shallow-rooted crops cannot access. When fermented, those minerals become immediately soluble and available to plants within hours of application. Research on fermented plant extracts has confirmed significant increases in soil microbial populations, accelerated organic matter decomposition, and measurable improvements in plant growth rates compared to untreated controls. The University of Hawaii's extension research on Korean natural farming inputs which are direct descendants of these medieval fermentation practices, documented 300% acceleration in organic matter decomposition and dramatic increases in nitrogen fixation and phosphorus solubilization in treated soils. The medieval farmer who steeped nettles in a barrel of rainwater was not performing folk magic. He was culturing a living biological amendment that cost nothing to produce and delivered results that modern commercial products struggle to match. Here is what the industrial fertilizer model cannot replicate. Not because the chemistry is wrong, because the system is missing. Each of the 7 methods addressed a different aspect of soil fertility, but their real power came from the way they reinforced each other when used together. The aged manure built organic matter and fed the microbial community. The wood ash corrected pH and unlocked the phosphorus that the manure had deposited. The compost pit processed all organic waste into stable humus that improved soil structure and water retention. The urine provided rapid soluble nitrogen that fed the microbial community between major applications. The green manures fixed atmospheric nitrogen and broke up compaction between cash crops. The fish waste and bone meal supplied concentrated phosphorus and trace minerals that the other methods could not provide in sufficient quantities. The fermented plant liquids inoculated the soil with beneficial microorganisms and delivered soluble nutrients in immediately available form. Remove any one component and the system still functions. Keep all 7 running and the system becomes genuinely self-improving. Each season, the soil organic matter increases. Each season, the microbial community becomes more diverse and more resilient. Each season, the soil structure improves, water infiltration increases, and the crop's access to nutrients expands. Medieval farmers did not achieve this through scientific understanding of soil chemistry. They achieved it through the accumulated observation of what worked and what failed over generations. The methods that built fertility were retained. The methods that degraded it were abandoned. What remained after centuries of selection was a system so effective that it maintained the productivity of European farmland for 1,000 years without a single purchased input. The modern equivalent of this system, organic farming with cover crops, compost and biological amendments, consistently shows that yields within 80 to 90% of conventional chemical farming are achievable after a transition period of 3 to 5 years. And unlike chemical farming, the organic system improves over time rather than degrading. The gap narrows every season as the biological infrastructure rebuilds. Medieval farmers did not have a fertilizer aisle. They did not have a supply chain. They did not have a corporation telling them their soil was deficient and selling them the solution. They had animals. They had fire. They had kitchen scraps. They had the river. They had the air above their fields and the biology beneath their feet. And from those 7 sources, they built soil that fed civilizations for 1,000 years without buying anything. The 7 methods are not historical curiosities. They are functional, scientifically validated, economically superior alternatives to a system that costs hundreds of dollars per acre per season, degrades the biological infrastructure of the soil with every application, and creates a dependency that grows more expensive and more fragile every year. The medieval farmer was not waiting for us to invent synthetic fertilizer. He was running a closed-loop biological system that we dismantled in the name of efficiency and are now slowly, expensively and incompletely trying to rebuild. The manure is still available, the ash is still in the hearth, the nettles are still growing along the fence line, the legumes are still fixing nitrogen from the same atmosphere they always have. The only thing that changed is whether we use them. Subscribe. Every week we dig up the agricultural knowledge, the biological systems, and the forgotten farming wisdom that the industrial food chain buried, not because it stopped working, but because it could not be sold. The soil remembers what we forgot. The question is whether we are willing to remember it too.